Okay, just to remind you where we were when we ended last time, we were in the process of extracting an approximate two-dimensional theory, and we showed rigorously that the energy we derived, two-dimensional energy, is actually the rigorous limit for small thickness of the three-dimensional energy. So it's not that we're replacing a three-dimensional theory by a two-dimensional theory. Instead, the conclusion is that the two-dimensional theory is actually the small thickness limit of the three-dimensional theory. So that's satisfying to know. And however, the cost, the price we pay for going from 3 dimensions down to 2 dimensions is an additional complication in terms of additional structure in the theory. So not only do we have a deformation, in this case, the midplane deformation, but we have these so-called directors, D and G and H, that we talked about, which give you information about the three-dimensional deformation in the vicinity of the midplane. And so if we continue to pursue this procedure, then we have to deal with those additional variables. And last time we ended by showing how the first director, D, which is the midplane value of the through thickness derivative of the 3D deformation, that can actually be solved in terms of the two-dimensional gradient of midplane deformation, grad R, and the plastic deformation at the midplane. We're assuming here that this has been frozen at a forward integrated value of the flow rule. We freeze the plastic deformation in the body and then minimize the energy with respect to deformation, and then continue the process as long as we want. Forward integrate the flow rule again and repeat. Okay, and I mentioned that in the case of pure elasticity, when you have plastic part of the deformation gradient is the identity, so that the deformation gradient is all entirely the elastic part, H. In that case, we recover classical Bernoulli-Euler, or in this context, Kirchhoff kinematics, where this director D is just the normal to the deformed mid-surface. And in the old days, people would invoke an assumption like this a priori, and then try to extract an approximate two-dimensional theory. But as we've seen here in this lead up to this point, such an assumption, a priori assumption, is overly restrictive. In particular, it's certainly not true in the case of plastic deformation, when plastic deformation is present, even in the case of pure bending, which is what we're looking at, a simple special case. Okay, so we have a procedure for computing this director field in terms of the midplane deformation and 2D gradient plastic deformation. The energy, however, remember, is proportional to this term here involving the moduli, R transpose, which is H because the stress is 0 at the midplane in pure bending. H prime involves F prime and K prime. So we need to think about K prime, that's the through thickness derivative of plastic deformation evaluated on the midplane. So it's not a derivative with respect to U, it's just a zeta derivative evaluated on the midplane and hence a function of U, midplane position. But this also involves F prime, which brings in a second director, G. Okay, so now we need to worry about G. We figured out what D is, but we have to worry about G now. And once we have G, well, we have the energy then, and then we can proceed to minimize it. Okay, okay, so R, on the other hand, so C is just some fixed moduli, some constants. R was H, which involves D. H prime involves F prime, which is grad D. D depends on grad R and K. So grad D, if you do a chain rule, will involve grad R, the second gradient of R, right? That's a third order tensor. and G also, in addition to K and K prime. So ultimately, at this stage now, this energy density is a function of these variables, plus K and K prime, which we're taking to be fixed in this discussion. Okay, so how can we find G? Can we find an expression for G and simplify this energy density further? Well, let's freeze all these variables. Let's freeze R of U, which means we're also freezing the gradient with respect to U and the second gradient. So we're freezing this as a function on the midplane. And define this function of G then at that frozen value of all these variables. Okay, that's just the energy density with a half in front here. And if you look back at your notes, you'll see that the potential energy, which includes the load potential, does not involve G at all in the case of pure bending. So having frozen these variables along with the plastic deformation, the load potential will just be some constant, the integral of some fixed functions. And then the energy, apart from the factor h cubed over 12, which I'll put on the other side, is then just this B of G, okay? And JK is fixed because we've frozen the plastic deformation in this discussion. So now the issue is we want to minimize the energy, right? So in particular, we should minimize it with respect to G, because G is one of the independent variables in this, one of the dependent, I should say, variables, independent at this stage of all the other variables. So to do that, we'll just implement the usual calculus of variations procedure, which we discussed at the beginning of the course. So you have let G of T be a one parameter family of G fields. And this will depend on U also, which is missing in the notation. Say G of U semicolon T, where U is midplane reference position. Then if this is going to be a minimum with respect to G, then it's also stationary. The energy is stationary at the minimizer. And to compute E dot, then we just see we have dB dG, vector G, inner product G dot. So this is a vector consisting of the components, the derivative of B with respect to the components of G, 3 components, and so on. And G dot here is arbitrary. There are no kinematic conditions that it needs to satisfy in the interior here of the plate. So the usual procedure then in calculus of variations is that, well, to refresh your memory when we first talked about it at the beginning of the course, in this instance we could take, for example, G dot to be proportional to dB dG, and then conclude that the squared norm of dB dG is 0 because its integral has to be 0, right? And so dB dG then is 0 point-wise in the domain. And that means the variation of B, which is dB dG inner product G dot, is also 0. So what we're going to do is solve this equation, hopefully in terms of G. This involves G, so hopefully we can eliminate it. Okay, so just to refresh you, R, which was H at the midplane, is F bar. F bar is grad R plus D bar, tensor product K, small k, then times the plastic deformation. This is being fixed in this procedure that we're describing. We're just varying with respect to G, small g. H prime, on the other hand, which is involved in the energy density, looks like this. So when we look at here the definition of B up here, and take a variation of this, take a dot of this, the only thing that's going to get dotted here is this G dot term, okay? So that will induce a variation of H prime, which we'll call H prime dot. So if we go through and take the variation of that definition of B, we have this. Okay, so we have a dot here and then a dot here. If we now invoke the major symmetry of C, we can see that this term is exactly equal to this one. And so the half drops out and we just get this. H dot prime, on the other hand, is just G dot tensor product K all multiplied by cap K, because that's the only thing that's being varied in this expression. And this is the same as putting the capital K transpose in front of this K. Let's call it L, okay? So then this B dot that we just computed is, we have the R transpose here in front of G dot, tensor product L, inner product moduli R transpose H prime. Let's see if we can clean that up a little bit. This is of this form, a tensor product of two vectors, inner product with some second order tensor resulting from the fourth order tensor operating on this second order tensor. So that has the structure. Say vector A, tensor product vector B, inner product second order tensor A. By definition, that's this. We can put the transpose of A transpose in front of the B here, in other words, A, take the trace that converts the tensor product to a dot product. So this is the same as this, so therefore this is the same as this, with the L now sitting on the right over here, okay? And then this is easy, we just use the definition of transpose to write this as G dot dot the transpose of R transpose, namely R, operating on this stuff. So this coefficient here of G dot must be dB dG. So we conclude that dB dG, the thing that's zero, because we're minimizing with respect to G, has to be this. And so this whole thing is zero because R is invertible, that means this is zero. So this is the equation we have to solve for small g. If we go back and work out what R transpose H prime is, it's equal to this. This involves an R transpose F bar, which involves the small d bar, and then a K prime. R transpose is the same as R inverse because R is orthogonal. R, on the other hand, is H at the mid-surface, mid-plane. H inverse F is just K inverse evaluated at the mid-surface. So we have this conclusion here, which on the right we have this K inverse K prime. So this is going to be an important term actually, because the through thickness derivative of K is what's going to induce the plate to bend due to plastic deformation. We'll see it momentarily. Okay, the rest is an algebraic problem then, how to solve this equation where R transpose H prime is this. And we see the G, the unknown, sits right here. That's the thing we're trying to solve for. Well, let's do the following. Let's define a second order tensor A, defined this way for any vector V. See, when you do this operation here, you're going to have C operating on R transpose G tensor product L. That's of this structure where V is R transpose G. So let's define a second order tensor this way with the same L here, which is K transpose small k. So it's also known for any vector V. You can use the major symmetry of the C tensor to conclude that this is actually a symmetric second order tensor. I'll let you do. You can work that out in components if you wish. It's pretty easy to do. Then if you take a further inner product with this arbitrary vector V, you're going to get this. By our previous calculation, that's the same as V tensor product L dot C operating on V tensor product L. Now, if you go back, way back in your notes, we talked about something called the Legendre Hadamard condition, which stipulates that this is strictly positive. L is a fixed non-zero vector. This is strictly positive then for all non-zero vectors V. So A is actually positive definite, therefore. and that means it's invertible. So this A tensor is determined by C, the given moduli, and L, which depends on the plastic deformation. So this equation we want to solve, namely this one, we want to solve it for this, can be rewritten then in this form, that A tensor, R transpose G, is equal to all this stuff. This stuff on the right-hand side does not involve the vector G. G is only involved explicitly here. So because A is invertible, we immediately get R transpose G as this. Then, of course, solve for small g by pre-multiplying with R and using R transpose is equal to the identity. You get this, so the same curly bracket here. R is H at the midplane, and H is F bar K. So now we have G in terms of F bar, which involves grad R, and D bar, which involves grad R and K. We have it in terms of grad D, which brings in a grad R and a grad K. And we have it also in terms of K prime. So we've algebraically eliminated the G vector. And with the plastic deformation field regarded as frozen in this calculation, the energy now reduces to a function, something that only depends on the midplane deformation. And we can then minimize the energy with respect to that midplane deformation. And the resulting equation that we get is the equilibrium equation for the plastically deformed plate. Okay, by the way, just to mention, you might be wondering, okay, let's suppose we can get K or capital G equivalently, the inverse of K, by integrating the flow rule in time, right? Incrementally for small time increments. And once we have it, we can even figure out its gradient with respect to U. But how about K prime? K prime is totally independent of K. These are midplane values. The value of the function at z equals 0 and the value of its derivative evaluated at z equals 0 have nothing to do with each other. So how would we update, if we can update K using the standard flow rule, how are we going to update K prime? Well, we can do that just by taking the prime of the flow rule, the zeta derivative of the flow rule. So just to illustrate that procedure, let's focus on isotropy, just as an example. Remember, G dot in time is a time derivative. G inverse is lambda, which is non-negative, times df ds. And for isotropy, that was deviatoric part of S. S, however, is 0 on the mid-surface in the case of pure bending, so this is 0. And that means G does not evolve in time on the midplane in the case of pure bending. If we take a prime of the flow rule, just using the product rule, take a prime throughout, G dot is 0. Df ds, which is dev S, is 0 because S is 0 on the midplane. We get lambda, the prime of Fs, using the chain rule. That's just two derivatives of F with respect to S acting on S prime, the through thickness derivative of S, evaluated on the midplane. So G dot prime then, this is the flow rule for G dot prime on the midplane. And so we can forward integrate this in principle, just as we forward integrated the standard flow rule. And because G here will be fixed at whatever value it was at time 0, toward T0. To get S prime, well, S prime from the constitutive relation, you just take the prime of the stress-strain relation. We assume the uniform material, moduli uniform, that would be E prime. E prime, E is the elastic strain, which is a half H transpose H minus identity. Take the prime of that, that's just the symmetric part of H transpose H prime, and H is R, rotation at the midplane. H prime is not. So this gives you the symmetric part, and because C has minor symmetry, we can dispose of the the qualifier sim here because this operation only picks up the symmetric part of R transpose H prime in the first place. And we know this in principle because we went to all that trouble of finding D and G in terms of R, small r, midplane deformation, then minimizing the energy with respect to R to get the equilibrium state. So we know this sometime. Then we can use a forward integration method to update G prime, right? Okay, so in principle, then we can update G prime and hence K prime. Knowledge of G prime is equivalent to capital K prime. Okay, well, this is this totally non-standard treatment I've been giving you here of plate bending in the presence of plasticity. And you won't find it in any textbooks, which is either a criticism or a virtue, I don't know which. But here's a justification for all this complication that we've gone through. Let's look at the tractions on the major surfaces, the top and bottom surfaces of the plate, where zeta is plus or minus h/2. The midplane stress is 0, if you recall, whereas the three-dimensional relationship between dW, dH, and Piola stress is this, right, which tells you that the JK Piola is equal to this. And if we take the prime of this relationship and then evaluate on the midplane, we get this. P is 0 on the midplane. And we get the prime of dW, dH, right, times K transpose, which gives you this by the chain rule, evaluated at H on the midplane where H is equal to R, K transpose, and then take the derivative of K transpose with respect to zeta, which is the same as the transpose of the zeta derivative. But in any case, dW dH on the midplane is 0, right, just from this equation. So we get this. We already know what this is from a previous discussion. Okay? And so if we operate this on K, which is the normal to either the top or the bottom surface, we get JK times P prime K is R times K transpose little k is L, if you remember. But all this is just dB, dG, and we went to all the trouble of solving this equation. That means P prime K is 0 because we satisfied this equation. Who cares? Well, let's see the implications. The traction at the top surface is the Piola stress at the top. I'll call it P plus, where zeta equals plus h/2. And the normal there is K. So if we do a Taylor expansion of P plus, that would be P at the midplane, z equals 0, plus h/2 times the derivative at the midplane, which is this, plus higher order terms, order h squared. This is 0 because P is 0 at the midplane. This we've just shown is 0 because we went to all the trouble of computing G. And so the traction at the top is of order h squared. At the bottom, we want it to be 0, right? But we can only guarantee that it's of order h squared, and that's, for a thin plate, that's going to be very small. At the bottom, the normal is minus K, pointing downwards. And we can do the same kind of Taylor expansion. This again will be 0. We just showed that this is 0. So we're going to get order h squared for that traction. If we had not gone through the unpleasantness of solving this equation for G, then we would have had tractions of order h and a much less accurate theory, because we started with the premise that there were no tractions at all at the top and bottom in the three-dimensional theory. This procedure guarantees that we can't guarantee they're 0, but they're approximate. They're very tiny. Whereas if we had not gone through this procedure, we would have had errors of order h, which are much more substantial when h is small. Okay, so what we've done is by eliminating these directors d and small g, we've enhanced the accuracy of the two-dimensional theory relative to the three-dimensional theory. And so that's our objective, is an accurate, we've made the theory, the 2D theory, as accurate as it can possibly be. Okay, so we've gone through that procedure. I mean, we haven't done it explicitly, but we know how to do it. We now minimize, the energy now depends on the R field, the midplane deformation, through its first and second gradients. So the two-dimensional theory is actually a second gradient theory of elasticity. You may have heard of strain gradient elasticity. That's a theory of elasticity in 3 dimensions that involves F, which is the gradient of deformation, and the gradient of F, which is the second gradient of deformation. Well, interestingly enough, the plate theory emerges as a second gradient 2-dimensional theory. That's another aspect, and that's another manifestation of the additional complexity of the 2-dimensional model. It sounds like a retrograde step. We've replaced a relatively simple model by a more complex one. But the great gain that we've made in doing that is that we're now solving everything on a 2-dimensional domain instead of 3D. That's far simpler. So we accept the extra complication because the analytical aspects of the theory are much simpler on the 2-dimensional domain. That's the same as in ordinary beam theory, right? I mean, in ordinary beam theory, the strain energy of the beam depends on the curvature of the center line, which is involves a second order derivative of the deformation of the center line instead of just a first order derivative. So in structural mechanics, we're accustomed to this kind of thing. Okay. Someone asked earlier, are we going to discuss beam bending? Well, here's an example in which we'll look at plane deformations. So here's the plate, let's say in the IJ plane, E1, E2 if you like, and K is E3. Here's the plate. Let's take it to be rectangular. And then we'll just bend it in the IK plane, right? So that if we just look at the IK plane, and then, so we have your deformation in the IK plane, and just translate it parallel to itself in the J direction, we generate the entire deformation of the plate. That's equivalent to beam bending, essentially. Right? So the further discussion here will just focus on the much simpler special case of plane deformation, like so. Okay. So here's our 2-dimensional position on the initial midplane in terms of X and Y coordinates, or X1, X2 if you prefer. And the deformation we seek then is essentially an in-plane part. We'll call it psi only of the X coordinate, a vector function of the X coordinate, plus Yj. Right? So if this means if we just take psi of X and parallel translate it along the Y-axis, we generate the entire plate deformation. And we'll take psi to be in the IK plane, which means its dot product with J is 0. So everything about the deformation will be known then if we simply solve for this single vector function of one variable X. So you can see it's a much simpler special case of the general theory. By no means the general plate problem, but this is a tractable, simple special case which illustrates some aspects of plastically deformed plates. Okay, the first order of business is to compute the gradient of this 2-dimensional gradient. As usual, use the chain rule. Grad U on du, grad R on du is dr. Dr, however, is d psi dx, dx plus j dy. Right? I'm not going to use a prime here for d psi dx because throughout this discussion, the prime means a through thickness derivative of some field, right? For example, capital K prime. dx, of course, is I dot du. dy is j dot du, so we can extract a tensor from this. And here's grad R. Okay, let's introduce a unit tangent to the deformed surface in the IK plane. Let's call that tangent T, so that's the xi dx. The xi dx will be tangential to this curve, right? As we know from a much earlier discussion. Take a derivative with respect to x of this position in the IK plane, you'll get a tangent vector. Divide by its norm and you get a unit vector, a unit tangent. Being a unit vector, we can describe it using an angle, let's say phi. And that will be some function of x because psi only depends on x. Cosine phi plus I plus sine phi k. So phi is the angle made between t and the horizontal here. You could insert that if you want. This is the angle phi between horizontal and t. So the xi dx is the norm of the xi dx times t. The normal to the surface then, which we discussed before, we obtained it using the Piola and Nansen formula. The normal is just this in terms of the same angle phi. This is k dot t, n is k dot t. Sorry, it's actually it's minus j coming out at you dot cross t, not k dot t. Okay, so to proceed, I need to know something about the plastic deformation. So let's pick one, plausible one. I'm going to pick one that induces flexure in the plate, induces bending. So let's have a quick look at the finite flexure problem that we normally study in a course like 185, for example, continuum mechanics. So I'm hoping that all of you have seen this discussion of finite flexure somewhere before. You can find a very nice treatment of it in Ogden's book on nonlinear elasticity, for example. So suppose you have a block, rectangular block, in the xz plane or the IK plane, and these axes here, these crossed axes, that's the line x equals constant, some constant, and here's the line z equals constant. And we'll suppose the block is symmetrically arranged around the x-axis, as much of it on above as there is below. You can imagine a flexure of the block then. Let's have a flexure of it. We just bend the whole thing into this shape. And intuitively, you'd expect then a flexure would take a line z equals constant and deform it into a ray theta equals constant passing through the origin, let's say. And likewise, a line x equals constant would be deformed into a circle r equals constant. So that let's investigate that possibility. Right now, we're not doing plasticity at all. We're just having a look at possible deformation. So a deformation like that would look like, take r as a function of x, so that when x equals constant, you get r equals constant, a circle. R along ER, take theta here, this angle, to be a function of z, so that when z equals constant, you get theta equals constant. And then plus yj into the board. And ER is our usual. ER and E theta, for example, are our usual polar unit basis vectors. So we can generate a deformation gradient from this in the usual way, chain rule. BR is r prime x dx. D theta is now theta prime z dz. And we have the dy. And dx now is I dot d capital X, initial position. dz is k dot d capital X, and dy is j dot d capital X. So we can extract the deformation gradient like so. And notice that we can factor out a rotation in front, a rotation that takes the ikj basis and maps it onto the er e theta j basis. That rotation would be this. And if you factor out in front, then in the square bracket, you just have I tensor product I, K tensor product K, and so on. Okay. Suppose the deformation is isochoric, so that the determinant of F is 1. This factoring out Q makes that an easy calculation because, of course, det Q is 1, being a rotation. And the det of this then, since this is on a diagonal basis already, is just r prime times r theta prime times 1. That has to then equal 1 if the deformation is isochoric. So that you can say something immediately if you take, so that r is a function of x under our assumption, so r prime is also, theta is a function of z. If you take a further z derivative, you conclude this is 0. And r prime cannot be 0 because if it were, then this top equation would be violated. So theta double prime is 0, which means theta is a linear function of z. So in particular, theta prime is a constant, a pure constant. And the figure above suggests that we take that constant to be 0. In other words, the farther up you go along the z-axis, the larger theta is, right? So we'll take theta prime, the constant theta prime, to be a positive constant. Then r theta prime would be r times that constant. Let's call that, since r is a function of x, let's call that some function of x, f of x. R prime then is 1 over r times that constant. So that's 1 over f of x. So a finite flexure has this structure of the deformation gradient. A rotation, a function of x, reciprocal, function of x here and 1 here, for some positive function of x. Okay, so that's a recap of the finite flexure problem. Purely kinematic discussion, nothing about constitutive equations. Let's assume our plastic deformation, evaluated at the midplane again, has this structure. So that we would expect, if our plastic deformation has the same form, somehow the plastic deformation would tend to induce a flexure of the plate itself, right? So let's look at that kind of plastic deformation. This has a determinant of 1, so that's consistent with plastic incompressibility, which is what you would get from a standard flow rule, right? So it's plausible, at least from that point of view. And let's introduce a rotation Q, which takes the IKJ basis into a new basis, tau, nu, and j, where tau and nu lie in the IK plane. So here's, so Q is taking our IK basis and deforming it into, deforming, say, a curve, horizontal curve, into a curve like this, with unitangent tau of x. We're introducing an angle theta of x that we'll specify later if we need to. And the normal to that, let's call it nu of x. So this then is a rotation. And as we'll see momentarily, here's our deformed shape, remember with that unit tangent t we discussed, unit normal n. We'll see later that our elastic deformation will map this basis into our deformed shape. Okay, so we'll see that momentarily. Okay, so this is a plausible plastic deformation. We haven't gotten it as the result of any flow rule, but it's conceivable that this would be the solution to a flow rule. In particular, it has a determinant of 1, which for plastic incompressibility. Its inverse is easy to get, right? Its inverse, this is very easy to invert and then put a Q transpose on the right. So we have this K field on the midplane. By the way, at this stage, we can note that, remember in the case of isotropy, which I'll confine attention to here, all constitutive functions, for example, the strain energy, are insensitive to the replacement of h by hq, where q is any rotation whatsoever. And because h is fk, that's equivalent to replacing k by kq, q is any rotation. So the constitutive functions for isotropy are insensitive to this replacement. So if you take the same Q here and multiply on the right, so you take this Q and multiply on the right by Q as indicated here, you get a Q transpose Q, which is the identity. And so the constitutive equation for isotropy should be insensitive to this Q we've introduced, and hence insensitive to the angle theta that defines Q. So ultimately, that should be a check on the calculation. The final expression for the energy density that we get for the plate should be insensitive to this angle theta in the case of isotropy. Okay, so now everything else is just a routine but tedious exercise. We need to figure out this D field, right? Like so. Notice then that grad R, remember that projection that we had last time onto the midplane. If you pulse multiply F by the projection, you kill off this K and you just get grad R. F, on the other hand, is HG, which is RG because H is R at the midplane. So we get this. D bar then, take this and operate on K, and you get RGK. So let's see, we have some information about G, right? We just introduced a G field corresponding to flexure. Just do this to it. G involved that Q and all this stuff. The 1 will annihilate the K term because this is a projection onto the plane with normal K, so it has this form. So the 1, the projection operation, will annihilate this term here, right? When we do this multiplication. And we just get this. Q1I was this tau tensor, and Q1J was J itself, and we still have an R multiplying. So we just have this. Grad R, on the other hand, from what we said before, is this. This is our unknown deformation, psi of x. So by comparing this with this, we could deduce that psi x is 1 over this F. F, remember, is associated with the plastic deformation, which I'm considering to be prescribed. Then psi x is that times R tau. But psi x is norm psi x times T. So immediately, norm psi x is 1 over F. Remember, F was positive. And T has to be R tau, right? And also, by comparing these two expressions for grad R, you get that J is equal to RJ. And that forces R nu to be equal to N. So R then, we can write as R times the identity in this form. R tau is T, R nu is N, RJ is J. And that's our expression for the midplane elastic deformation. So that is consistent with what we said here, right? So the elastic deformation maps this basis onto this one. This was associated with the plastic deformation, and this is the final configuration here. Okay, what about K prime? Well, K at the midplane doesn't tell us anything about K prime at the midplane. To get an appropriate expression for K prime, one thing we could do, just by way of illustration, is to take the K that we had above, namely this one, in which F is a function of X, and extend it to a function of zeta, this zeta coordinate, off the midplane, right? Instead of taking K to be only a function of X, let's take a three-dimensional K, K tilde, put a function of F of X and zeta, F of X and zeta, and leave everything else the same. Just to get an illustrated example. So we do that here. Then take a prime of that, and that's a zeta derivative. When you do that, nothing else. So the Q will leave it as just a function of X. take the prime of that, take a zeta derivative, you get this. Evaluate on the midplane, and we get f prime, which is the value of this zeta derivative when zeta equals 0. And you get this. Let's see. That makes sense also from the point of view of plastic incompressibility. Let's see why that is. Well, if you were to compute the derivative, the zeta derivative of jk, you get cofactor k, inner product k prime, all evaluated in the midplane. This is the same as determinant k, and this then is k inverse transpose. The dot gives you this, so this is k inverse, g is k inverse. And so we need the trace of this, but if you look at the k prime we've just introduced and multiply it by g, after a line you will get this, and that has 0 trace, right? That has 0 trace because this is purely diagonal and those terms are opposite each other, plus and minus. So jk prime is 0. And that's consistent with plastic incompressibility throughout the entire body in 3 dimensions. Because if you differentiate this, first of all, if you evaluate this on the midplane, you get 1, as we had before. But if you take any order zeta derivative, right, d n jk d zeta n, right, any nth order derivative, you'll get 0. This is an identity, right? This is an identity. So this is consistent with overall plastic incompressibility in the 3-dimensional sense. Note, however, that this f prime here, which appears in k prime, this innocuous little scalar here, f prime, is what's going to drive the bending. It's going to induce the bending of the plate. This is a midplane value, hence a function of x alone. Okay. Okay, so the rest is just fairly routine. To specify the energy density, we need this R transpose H prime business. Right? We can replace R by H because H is R at the midplane. H is Fk, so take the transposes. H prime is F prime K plus Fk prime, and just carry out the product. And we have, I can restore the R here in this last term. And remember from our previous calculation that this term is just K inverse K prime, which we now have an expression for. All the rest of it is fairly routine, and you get this long expression. Straightforward. To proceed, we need the director D, which from before is this. And if you go through our previous results, you will conclude ultimately that that's just this F from the plastic deformation times the normal to the deformed surface, the actual surface that you see in the deformed configuration. So here we have a director that's aligned with the normal, but not equal to it. Okay. So it's not quite the Kirchhoff kinematics, because if it were, this would be a 1. So plastic deformation, again, deviates from the classical assumption of Kirchhoff or Bernoulli-Euler kinematics. Now that we have D, it's a simple expression. You can take its 2D gradient, and we get this, F grad n plus n tensor product grad F. F is only a function of x, so that's df dx I, and we have this. And we need, let's see, for example, grad D transpose on D. Grad D transpose is this. Operate on D, you get grad n transpose on n. That turns out to be identically 0, which you can show for yourselves because n is a unit vector. So for example, ni is equal to 1 in Cartesian. So you differentiate that, you get ni comma j nj. Sorry, ni comma j ni is equal to 0. And that's the component form of this right here. So this is just this, relatively simple. We also need grad R transpose grad D. That's a bit more complicated. Using our previous results, let's see. The only complication is grad n. To figure out what that is, let's use the chain rule. Grad n du is dn. N was minus sine phi I plus cos phi k. Take a derivative of that, you get this. Phi is a function of x. So that's this. And you can extract grad n. This d phi dx. Now, d phi dx is like a curvature. It tells you the rate of change of the angle as you move along the x-axis. It essentially contains information about the deformed shape of the plate. So that ugly term that we need to figure out turns out to be this one up here is relatively simple. It's just this. And to find g, we do this operation in which we now pretty much know everything on the right-hand side. For example, this term, R transpose grad dk, here's a calculation that goes through that in detail, and I won't bore you too much with that. But you can do it easily, and you deduce this, where this tau, and nu were those unit vectors associated with the rotation factor in the plastic deformation. We also need this k inverse k prime term here. And after a little bit of effort, you find that here, okay? So again, F and F prime are associated with the plastic deformation that we're taking to be fixed in this calculation. And after a lot of tedium, you then get this expression for this thing, which sits inside here. And now you can, if you know the elastic properties, and you know, therefore you know A, you can invert to find G. And I'm actually going to let you complete this calculation in homework, in your new homework, your new and final homework problem. So for example, isotropy, you know that C on B, on any tensor B would be, you know, for example, the stress-strain relation, take B to be the strain, you'd have lambda trace strain identity plus 2 mu times the strain. For any old B whatsoever, this is the expression for isotropy. So then you need to find, from this you can compute this capital A tensor up here, and then find G, because now you know C. Now you know what C does to any arbitrary tensor for isotropy in terms of the Lamé moduli. You can find A from its previous definition. You can find G, and therefore you can construct from everything we've done here, you can construct R transpose H prime, and therefore get an explicit expression for this energy density. And then the strain energy would be this 124 H cubed factor integral over the midplane. JK was 1, remember, for our plastic deformation that we assumed. Let's take a plate of unit depth in the y direction, into the plane, into the screen, and of length L in the x direction. That would be dimensionless L, capital L. Then this whole energy would reduce to this. You would find this energy density will depend explicitly on x because of this function f of x and f prime, a function of x that have been appearing throughout this discussion. And it will depend on the deformation through this angle phi, the deformed shape, the angle it makes with the x-axis, the derivative of that angle with respect to x. And that energy density will turn out to be quadratic in d phi dx because this is a quadratic form. It'll have this structure. The coefficient will be some function of x here, some other function of x here, and a final function of x here. These will, you will find these depend on the Lamé moduli because of the modulus here, and the plastic deformation through f of x and f prime, which I'll call g of x, so you don't think of this as an x derivative of f. It's just a different function of x, right? It's the zeta derivative of f evaluated in the midplane, some other function of x. And it'll turn out that a of x is positive. You'll see. Okay, so that's the strain energy. Equilibrium says that the total potential energy should be stationary, and the dot is the variation. Stationary at equilibrium, okay? From this, we should be able to extract the equilibrium equation. And so here, we can compute a variation of the strain energy. The strain energy is some function u of d phi dx. The variation of it is this, du d phi dx times the variation of that. And then we can simply do an integration by parts, as we usually do. Okay, that's an x derivative of d phi dx phi dot minus the x derivative of d phi dx times phi dot. This get integrated out to endpoint values, and you're left with this. To keep things simple, let's suppose that we clamp the left end so that we specify the angle that the deformed plate makes with the x-axis at x equals 0, right, which is along this edge here. So let's say we fix that at the value, say, phi naught, and then we don't allow any further variation at that point, so it's clamped there. Then the lower limit here would disappear, right? This equation says that the variation of the load potential equals the variation of the strain energy. Well, you can see that this will accommodate this example of a load potential. You could figure this out in terms of the load potential we derived before, involving those through thickness derivatives of Piola attraction and so on. But you can see immediately that this statement will, for example, would permit a load potential of this form, L, not the same L here, sorry for using this notation. This L is a load potential, this is a length, right, dimension. If we take a dot of this where m bar is some fixed quantity, then we get phi dot at L, which is exactly what we have here, right? We could regard m as a bending moment applied at the end, x equal L, all along the edge, x equal L. And for example, we could take m bar to be a fixed number so that the variation of it would just be m phi dot at L. That's not the most general thing we could do. We could take L to be a function of phi at L, and then L dot would be the L d phi at L phi dot, and then this m bar would be, could depend on phi at L. So you could have a variable moment. But this is just the simplest example. So then this would just be this. Remember, there's this factor of 24 over h cubed business. That would be this, where m is defined here. Then the equilibrium condition would simply say this, be equivalent to this. And if phi dot at L is unrestricted, what we could do is we could say, let's consider we consider phi dot, consider variations phi dot that are 0 at L and at x equals 0. Then we'd have this equals 0 for all such phi dot. We would then obtain this equilibrium equation. With that satisfied, the second integral would be gone, and then this would have to be 0 for all phi dot L. Well, suppose there's no kinematic condition prescribed at x equal L, so that this would be arbitrary. Then the square bracket would have to be 0, which gives you the so-called natural boundary condition. So this tells us that the bending moment in the beam or the plate is just equal to the prescribed value at x equal L. And the equilibrium equation, this is moment equilibrium, the bending moment on a cross section corresponding to constant x, is constant throughout the plate. That being the case, that constant has to equal this constant. So this is true throughout the plate. On the other hand, from the expression for u that we had, the derivative with respect to phi x is just this. Remember, it's quadratic in phi x. It's just that. So we can equate this to this, m, given constant, and we get the derivative of the deformed shape, the angle that specifies the deformed shape. Integrate that, and you get the angle phi of x that specifies the deformed shape of the plate, very simply. Okay? Where everything here on the right-hand side depends on the elastic properties and the plastic deformation field that we introduced. So I'm going to ask you to complete this in your homework. By the way, you might be wondering, well, what about force equilibrium? Here we've picked boundary conditions that allow us to immediately write down moment equilibrium and integrate it instantly. If we wanted the equations of force equilibrium, what we would do is remember that psi dx, because psi was the deformation, is related in this manner to the angle phi that we've just discussed. So a variation of that, F is fixed, remember, we have this formula for the variation. We get F, the normal to the deformed surface, times phi dot. So the phi dot that appears in this variational statement could be replaced by this. So that would be an x derivative of the variation of position. And then in that integral in the variational statement, we could just carry out a further integration by parts to eliminate this and get everything in terms of psi dot. This would be like a virtual velocity. And so whatever multiplies it in the variational statement would be a force, and that we get force equilibrium that way. Okay. I won't bother to do that here, but you could do that if you want to. What about the unloaded shape? Well, let's say we don't specify any bending moment at all. We would specify it to be 0. Well, the initial shape of the plate is just a flat plate, right? But due to the presence of plastic deformation, the unloaded shape will not be flat anymore. It will be this function of x. Okay, this is our boundary condition value. So U stands for unloaded here, unloaded shape. We get a curved unloaded shape due to plastic deformation. And in fact, if B of x were 0, then phi unloaded of x would just be phi naught, and then the plate would remain flat. In homework, I'm asking you to show that the only way that can happen is if little g of x is 0. The little g stood for f prime, remember, the through thickness derivative of the plastic deformation. So it's that through thickness derivative, f prime, that is crucial in causing the unloaded deformed shape to be non-flat, right? So this is exactly what you do when you make a part in an industrial process. You take a sheet of metal and you deform it, you bend it to make, say, a panel for a car body or something, and then you unload it. You take away, in this example, take away the bending moment. You'll have a residual shape, which is given by this. By the way, the people in this field talk about also a springback, so-called elastic springback, which is the loaded shape, take away the unloaded shape. That depends on how much you loaded it by. Just by subtracting what we had before, so subtract this phi u from what we had a moment ago, you'll get this. So in your homework, I'm asking you to find those coefficient functions in the energy, a of x through c of x, a of x, b of x, c of x, in terms of the Lamé moduli, and these functions that specify the plastic deformation, to show that the plate remains flat if this f prime is 0, so that to get a curved unloaded shape, you need a through thickness derivative of plastic deformation, which makes sense physically. And just to simplify the calculation, I'm asking you to set f of x identically equal to 1, and just have f prime a non-zero f prime, non-zero g of x. This will greatly simplify all those formulas that we've just been going through. And then I'd like you to figure out, for a given g of x here, what would this unloaded shape look like in that case? Right. Okay, and that's it. So I'll stop a little bit early here. Next week, we'll get onto a new topic, which will be how to model strain hardening in materials. We'll talk about some classical models and then some much newer models, non-classical models. And that will segue into a discussion of crystal plasticity, which will take place in the final week of the semester. Okay. Any questions?